Okay, so we're going to take a look at how to evaluate a definite integral when u substitution is involved, okay? So what makes this a u substitution problem is the fact that I have an inside and an outside function, okay? So I've got x cubed minus 1 inside of parentheses to the third, and then this is an outside thing as well. So we're going to go ahead and say that u is equal to the x cubed minus 1, because that's what's contained inside of something else, right? Then we want to find the derivative of that, the du, which is 3x squared. The derivative of 1 is 0 times the dx. And that 3x squared dx matches up perfectly with this. We have a 3x squared times a dx right here. So that's going to get replaced by the du. So these two things will disappear and become a du. This is going to be u to the third power. So when we rewrite this function, we're going to have the antiderivative of u to the third du. All right. Now notice I'm not writing the bounds there, and that's because the bounds are x values, and there are no x's in this expression. I'll come back to the bounds after I finish doing the integration process. Okay. So now that I have the rewrite in terms of u's and du's, I want to go ahead and find the antiderivative using the power rule. So this is equal to u to the fourth power over 4. Normally I would write a plus c, but because I know that I'm eventually going to have bounds to plug in, I'm not going to write the plus c here, right? So now I can go ahead and replace the u with the x cubed minus 1 to the fourth power over 4, and we can evaluate that with our bounds from 0 to 2. Okay? So here's where I'll go from there. The 2 goes in first. So I'm going to have 2 to the third minus 1, raise that to the fourth power divided by 4. Okay, so that's my first number. Subtract, I need to do 0 to the third minus 1, that whole thing to the fourth power divided by 4. Okay, so let's see. 2 to the third is 8, 8 minus 1 is 7, 7 to the fourth power is, good question, 2401 over 4. Okay. Minus 0 to the third is 0, minus 1 is negative 1, negative 1 to the fourth is 1 over 4. So this comes out to 2400 over 4, which is the same thing as 600. So the final answer is 600. All right, and I want to remind you that 600 represents the area under the curve. If I were to graph this function right here, if I graph 3x squared times x cubed minus 1 to the third, if I graph that and look at the interval from 0 to 2, if I shade the area under that curve, meaning between the curve and the x-axis, it'll come out to 600 squared units. Okay. Now there is another way that you could approach this problem. And that is if you wanted to go through a process to find new bounds instead of going back and using the 0 and 2. Okay, so here's how I would do that. Back here, I could have said, well, I'm switching everything over to u's, why not find new bounds that match the u values? So the top bound was a 2, so think of it like function notation. What is u of 2, okay? So think of this as being like u of x equals like f of x equals. That would be 2 to the third power minus 1, which is 8 minus 1 is 7. So that means the 7 could replace the 2 if I wanted, right? And then I could also figure out, well, what's u of the lower bound, 0. So that's 0 cubed minus 1 is negative 1. What that means is that back here, I could have approached it a little bit different. When I had u to the fourth over 4, instead of going back to the x's, I could have evaluated that from negative 1 to 7, and I would eventually end up with the same thing, because I would get 7 to the fourth over 4 minus negative 1 to the fourth over 4, which is exactly what I ended up with right there. So it would lead me to the same work. It's just doing these computations, the 2 cubed minus 1 and the 0 cubed minus 1, off on the side separate, okay? So on some of the examples, you'll see me do this new bounds idea, and on others, you'll see me go back and all the way to the x's and use the original bounds, okay? But there are 2 ways to do every single problem. So you just need to pick which method makes the most sense to you and run with it. All right, that's example 1.